Okay, breaking the comic relief here. Y'all ready? All right. So Unit 11 is going to take off from exactly where Unit 10 left off, and now we're introducing the concept of acids and bases to the whole rice table thing. Thanks for the pencil sharpener. That was awesome. All right. So first thing we're going to have to do is just define what acids and bases are. There are a couple of different theories of acids and bases, or different definitions that you guys are going to be responsible for. The first one being the Arrhenius acid and base theory. The Arrhenius acid and base theory is just a different definition than Bronsted Lowry. So Arrhenius acids are substances that produce H+ in solution when they're dissolved. Okay, and an Arrhenius base is a substance that produces an OH- in solution when it dissolves. Just know that definition. Not hard. And this brings up to the concept of water, and water self-ionizing. And this is a really, really important concept because it leads to the entire pH scale. So if I were to have water self-ionize, water would have water liquid dissolving into 2 ions, right? Now if I were to say, please write the K expression, products over reactants, you have your products. Why don't we have over anything? Why isn't anything on the bottom? Because it's liquid, right? So this is the K expression for water. Because it's the K for water, we put a little W and call it the KW. This is something you need to know, a little equation that will help you go back and forth between the hydronium and hydroxide ion concentrations using the KW. You need to know the value of the KW as 1e negative 14. And that's not hard to remember, and I'll tell you how. The entire pH scale is based off of that number and this expression. So, you know, we don't know for sure if it's true. I believe that this dude named Sorensen, he was someone who worked in the beer industry. And a lot of teachers I hear say, oh, soda pop or something. I'm like, you guys can handle that he worked with beer, right? I'm not ruining your youth or corrupting y'all. So beer, it's beer. Beer. So his whole deal was he got very tired of recording a lot of this data that had lots of large exponents and such. So he came up with the logarithmic system. And if you look on your next slide, your next page, he decided that the pH system would be taking negative log of the H+ concentration, and then the pOH system is negative log of the OH concentration. So if you look back at this number, knowing your log rules, that's why you had to have taken Algebra 2 to be in this class, what would the log of that number be, the log? Not 14, negative 14, right? So we take the negative log of it, we get 14. You're going to have to know for the non-calculator section of the AP how to do your basic 10-based logs, your real simple ones. But we know that the pH scale goes to what number? 14. So it's going to be easy for you to remember that KW, and you do need to know it. All right? So if I had a situation where we know that KW is equal to H+ times OH-, if I had a situation where I had totally neutral water, where I had equal concentrations of both of these, what would each concentration be? What? Correct. And that would be 1 times 10 to the negative 7. Okay, what's the negative log of that number? 7. What's the pH of neutral solution? 7. See, it all ties in. Okay, so it's all based on that KW expression. So not only do you need to know the KW expression, you need to know all of these. And pOH plus pH equal to 14, they're complementary systems. Once you know one, you can easily find the other. pH is the one we're going to be using the most. pOH is more of a route to get to pH, but you still need to know it. And we know that under 7 is acidic, greater than 7 is basic. You can have negative pHs, and you can have pHs over 14. It's actually pretty common, so don't let that freak you out if you see that, okay? Okay, so what we're going to do for this first thing is we are going to write some equations. We're going to write dissociation equations where these things ionize in water. And then you're going to tell me if this is going to be an Arrhenius acid or base with that using the definition of Arrhenius. The first thing, though, we need to do in order to write a proper equation is to tell me the strength of what we're looking at. What's the strength of HS? It's a weak binary acid. So you're going to write your HS. When anything is weak, any acid or base is weak, it can't dissociate 100%. So it's going to be in equilibrium. Because it's in equilibrium, I need to see your double-headed arrows. And then you've got your ions. And is this an Arrhenius acid or base? We're producing an H+, so it's an, we're going to say an Arrhenius acid. I'll just write the word acid. I won't write Arrhenius every time, but that's what we're looking at. Okay. What is this one, strong or weak? Weak because it's carbon containing. It's organic. So this is going to require an equilibrium situation. And we get H+ plus C2H5O-. Is that an Arrhenius acid or base? Acid. Okay. What? Oh, C6. Thanks. C6H5O-. I'll just rewrite it because that looks really ugly. Well, I did it here as well. That's why I copied it wrong. Okay. I don't like C. Let's just go to D. D, strong or weak? Strong. So since it's strong, it's going to dissociate 100%. So we're going to have a single-headed arrow making the two ions. Is this an Arrhenius acid or base? Good. Agua. Strong or weak? It's definitely weak. And we know it is because didn't we need to write a K for it? So it's got to be weak. And then what is it ionized to? H what plus what? H plus OH minus. Is this an Arrhenius acid or base? Arrhenius acid produces H plus. An Arrhenius base produces OH minus. Which one is it? It's both. Who remembers what you call something that's both? I'm going to be really impressed. No one did third period. She got it. Hannah got it. Amphoteric. What were you saying? What? What did you say? Something. Did you say autoionization? Is that what you said? Oh, polarization. No, you're way off base. But at least you got amphoteric. Last period I wrote all the way out to the, and then they said amphibian. I was like, no, it's not an amphibian. So they were really out on a limb there. All right, I want to make a note about F. F is carbonic acid, and it's a polyprotic acid. What does that mean? Well, actually, no, it doesn't mean two protics. Many protics. If you have, and what's protic? What does that refer to? What does protic refer to? Proton. Okay, what is a proton? What's a proton? A positive particle. Okay, what in here could be a proton? H plus. Why is H plus a proton? What's in a normal H atom? One proton and one electron, right? So when this becomes positively charged, what's left? A proton. So another way to say H plus is to call it a proton. So this is a polyprotic acid. Whenever you have a polyprotic acid, you lose H's one at a time. So you just don't pull both H's off. All you're going to do is take off one at first. And this is a weak acid because it's carbonic, so it's going to be at equilibrium. And so you get H plus what? H CO3 minus 1. And then an additional step will happen where you have your HCO3 minus 1, and it's going to lose another H. Okay? So what's important about this, and we'll do more with the math to prove it, but if I were to find the pH of a solution, pH, I need the H plus concentration. The first H contributes pretty much all the H plus that matter. If I were to figure out the concentration of the second H plus and add it to the concentration of that H plus, this would be so teeny, it wouldn't even change the number enough to change the pH at all. So this first dissociation is the important one. And we're going to be ignoring the other dissociations after that, okay? So always just write first dissociation, unless I ask you to give me the multiple equations. We will do math to prove that later. So now we get to do some math, and we're going to split this up because there's so many problems, and I want everyone to try a different one. I'll do A with you, and then you're going to put this in your calculator on your own. What we're trying to find is calculate the pH and pOH of all of these solutions. We have 6 of them to do. We know that pH is equal to negative log of what? H plus concentration. So in a case like A, all I need to do is plug that concentration in and solve. Now here's the kicker about pH and significant digits. How many sig figs are in this number right there? 2 sig figs. When you're looking at pH units, significant digits are only the decimals. So for a 2 sig figs in pH, I need 2 decimal places. That will probably come out to be 3 numbers, which doesn't look like 2 sig figs, but you don't count the first value in pH when you're looking at sig figs, okay? So someone plug that into their calculator and tell me what they get. 2.8. See how that feels like 3 sig figs? It's not, it's 2. And I can't remember, y'all can help me with the algebra terminology, but part of the log, I can't remember if it's the abscissa or the mantissa, is what dictates this number. And that has nothing to do with how accurate your value is read, how good your pH meter is, okay? All right, so how do I find pOH? Because I need that as well from this number. 14 minus that, and what do you guys get? Good, 11.15. So if I get to a problem like B, and I'm going to let y'all break y'all into groups real quick by rows, you're going to do some of these. If you start with the OH concentration, what do you end up calculating first? Negative log of that would be what? pOH first, and then you could get pH from that. So what you start with first is dictated by what you're given first. All right, so Annie, S, y'all's row is B. Jasmine, y'all's row is C. Y'all are D. You guys are E. And you guys are F. That worked out perfectly. All right, so I'm going to pause the video, and then we'll get all the answers up. Okay, so these are the answers. Everyone in their row did their problem and say these numbers are correct. So any questions on going from concentration to pH or pOH? Simple, yeah? Okay, now we're going to go the other direction. Given the pH, we need to find the H plus and the OH concentration. With this, again, I'm going to do the first one with you. Really quick, let me explain what's going on. We know that pH is equal to the negative log of the H plus concentration in moles per liter. Before, we just plugged in the H plus and solved for pH. This time, we are actually going to plug in the pH and solve for the H plus, which is a little bit more algebraically challenging. But with the advent of our awesome calculators, I'll show you how to rearrange the equation, and so you can do it really quickly. If I want to isolate H plus, I'm going to go ahead and get negative on the other side. So I get negative pH is equal to the log of the H plus. How do I get rid of a log? 10 raised to that. So I do 10 to the negative pH, and that gets rid of that, and that's equal to your H plus. So your keystrokes in your calculator are second log, the little negative sign, not the minus, the negative sign, and then your pH or pOH value. And that'll give you your H plus or your OH concentration. That's how you enter it in the calculator. All right, we got to also watch the sig figs. This is a pH given to you in 7.41 is going to dictate we have a concentration with 2 sig figs in it. So watch yourselves. So when you plug in 10 to the negative 7.41, what do you get? I got 3.9 times 10 to the negative 8 moles per liter. That's equal to what concentration? I did pH, so it's equal to H plus. How am I going to get OH concentration? And I don't want you to calculate POH to do that. There's a way you can do this in one more step. How can I get from H plus to OH minus? The KW, right? And so remember, KW is equal to the H plus times the OH minus. So you're going to use 1e negative 14 and divide that by your H plus concentration. And you're going to get 2.67 times 10 to the negative 7 moles per liter. And that's equal to your OH. Notice I'm having units on this. Concentration, I do want to see units. pH doesn't require units. They're pH units. Okay? All right. Rows, take your same letters. There's still the same number of options. And start getting some answers for me. More? All right, so those are the answers that I got for all my OH concentrations and my H plus concentrations. If you have a chance to need more practice, just jot down the answers and you can go do the problems that your row did not do with you. Okay? So these are obviously calcs you did in Chem 1, but they're crucial because they're going to lead to some of the more complex stuff that we're going to hit later this unit, okay? All right, moving onward to our next definition of acids and bases, and that's the Bronsted Lowry. Some people say Lowry Bronsted, doesn't matter. But basically, again, they're bringing up the use of the word proton. A proton, again, is that H plus. It's interchangeable. So an acid is defined as a substance that donates a proton, and a base accepts a proton. You have to know this. We're going to be going back to that a lot. So looking at this example, you're going to have to identify acids, bases, and conjugate bases. Because we're donating and accepting a proton, your things on the left here are going to differ with the conjugates only by 1 H. So if you look, this is our acid. What on the right side is only differing by an H? Cl minus. So this is a first conjugate acid-base pair. This is the acid. That's the conjugate base. Why is Cl minus a base? Well, if you look at it going in the other direction, what does Cl do to get to HCl? It accepts a proton, and that's the definition of a base. So it's acid conjugate base, and my other pair, base conjugate acid. Okay? So let's go on. I don't know why these slides are in this order. This just talks about strong acids versus weak acids, and the next one is strong bases versus weak bases. We'll cover that, no worries. But it says, number 4, for each of the following acids, write the formula of the conjugate base. All right, since these are acids, what are acids? Proton what? Donors. So they're going to each give up a proton to make a conjugate base. So H2PO4 minus, what does it do? HPO4 minus 2. Down below, HClO2. What's that called? Not chlorite, but chlorite is chlorous acid. Let's review that nomenclature. Yikes. All right, so what does that make? What's our conjugate base here? Good. H2O acting as an acid becomes OH minus. Now, don't let this one scare you, okay? People on the AP freak, and national average on anything with one of these nitrogenous bases is really, really low because people freak out. Nitrogen is the center here. This is the crux of what's going on. Nitrogen has 4 spots around it. On the nitrogen right now you have a methyl group, a CH3 hanging off, and then you have 3 H's, okay? For it to donate a proton, it's going to donate one of those. Don't go pulling stuff off the methyl. It's going to donate from one of its spots. If it needs to accept, it's going to accept onto the end. So all you're doing is taking off or adding an H at the end. But I want you to realize this is a nitrogenous base when it's not charged. But remember those 4 spots. So with that being said, this is going to donate and become what? NH2 with no charge. All right, OH minus. This is a trick. For each of the following acids, is that even an acid? Did you just go to me? That was kind of cute. All right, so this is a trick. This is not an acid. There is no way in heck you're going to easily get OH minus to give up its H. Okay, and the last one, NH4 plus the ammonium ion. What does it become? Ammonia. Good. All right, next slide. Now we're going the other direction for each of the following bases. So bases are proton. Proton lovers. What are they? Proton acceptors. I don't know if I spelled acceptors right. I really can't spell. So what does OH minus become? That we know is a base. So what's its conjugate acid? H2O. Cl minus becomes CO2 minus 3 becomes, I said CO2 minus 3, didn't I? Yeah, it's CO3 minus 2 becomes HCO3 minus. Water, when it accepts, becomes the hydronium ion. Oh, there's a nitrogenous base. Are you going to freak out? No, you're just going to throw on another H to that 4th spot because this is 1 spot. 2 spots are taken up with each individual H, so we have place for 1 more. And it's called what? Not called what? What's the formula? Plus. All right, this one, this has a free spot, so what are we going to do? Throw an H on the end, and we make N plus. Good. All right, keep moving. For each of the following compounds, we're going to write the reaction with water, and then you're going to indicate whether or not it's, well, you're just going to label acid base, conjugate base. So HCl, we're going to mix it with water. Which one's going to be the acid and which one's going to be the base? Good. HCl will be the acid. That makes this the base. HCl, strong or weak? Strong. So what does that tell you about my arrow? 1 arrow. So if the acid is the proton donor, what are my 2 products? Cl minus and H3O plus. Cl would be your conjugate base, and H3O plus your conjugate acid. Yay. Ammonia. Huh. What's ammonia going to be compared to the water? Ammonia is going to be the base, the water is going to be the acid, because water is amphoteric. Is ammonia strong or weak? No, weak. It's one of my most famous weak bases, okay? And then we're going to make, since that's a base, it's a proton acceptor, so what do we make? NH4 plus OH minus. So NH4 is the, and this is the conjugate base. All right, next up, HCN plus water. HCN is going to be the acid or the base? And this is going to be the base. Is it strong or weak? Weak. So we're going to donate an H to water to make CN minus plus the hydronium. This is the conjugate base. This is the conjugate acid. Okay, this next one. Save some room. I'm just going to add water here. This H, blah, blah, blah. What's that going to be? Acid. This is going to be base. Strong or weak? Weak. So we end up getting C6H5O minus plus H3O plus. This is my conjugate acid. That is my conjugate base. And the last one on the page, our infamous nitrogenous what? No, nitrogen. This is a nitrogenous base. Okay. Ever heard of your amino acids and the pairing, your base pairs? Base, nitrogenous base. That's all based on the biochemistry. I'm not making that up, I promise. All right. What am I going to, did I see a hand? No. All right. This is going to be a base, so it's a proton donor. What do I end up, proton acceptor, excuse me. So what do I end up making? CH2, NH3 plus OH minus. So this is my base. That's my acid. That makes this the conjugate acid and makes this the conjugate base. Okay. Less scary than last year. Conjugates always freak you out first year, and when you get to second year, it's like, oh, that's really not that bad. All right, so this is the whole point of what we're doing. Starting in this unit, you're going to learn to take the pH of different things. Today, you're going to learn how to take, and I'll start my little list, the pH of a strong acid base. So that's number one on my list. And by the end of the next 2 units, we'll have the pH of strong acid bases, weak acid bases, salt solutions, buffer solutions, and something I call invader problems. So this is the first thing we're finding the pH of. So we know that pH is equal to the negative log of the H plus concentration. Well, what's the only concentration that I actually was given in this problem? Of HCl. I don't have concentration of H plus, so how am I supposed to find pH? Any ideas? Well, what can you tell me about HCl, what type of acid it is? It's strong. So what happens when it's strong? I heard balanced equation. I like that. It completely dissociates. 100% of it is going to dissociate. So if I have a liter container and I have 0.450 moles per liter of this, if every single one of them splits up, how many of each of these am I going to have? 0.450 of this and 0.450 of that. It's because it's strong that we can make the assumption that the H plus concentration is equal to the concentration of a strong acid, or the OH concentration is equal to the concentration of a strong base. It's only because it's strong. So because of this, all we have to do is plug in the acid's concentration. And to 3 sig figs, what is my pH? 3 sig figs. 347. No units are necessary. Did you see what I did here with the colors? Anybody get this? I didn't mean to do that. See? Why? What am I doing the colors of? For what? With what? Litmus. Yes, litmus paper. Y'all are like, what did she say? I want to hear it, Raina. What'd you say? The American flag. Yes, because I'm proud to be an American. Actually, this is the Texas flag. All right, so KOH. They're giving us something with a concentration of 0.710. But I need to find pH. Am I going to find pH directly? No, I'm going to go for pH first because that's equal to the negative log of the OH concentration. KOH strong or weak? Strong, so I get K plus OH minus 100%. So what's my assumption? That 100% dissociates in solution, and so we have the same concentration for each of these. So I plug that into there, and I end up with a POH 0.149. Is that what the problem's asking me for? Nope, the problem wants pH. subtract from 14 and I get and that is it. So tomorrow we're going to go into weak acid and base stuff. It's going to be really short tomorrow, shorter than today. And you still even have time today, so I'm just too nice to you people.